Hi everyone. In today's video, we will analyze the distribution of cybersecurity incidents across different industry sectors using the Shannon and Donsker-Varadhan representation of entropy in R. In information theory, entropy is a measure of uncertainty or randomness. Now, in cybersecurity, we often apply this concept to data in order to understand the predictability and distribution of different attributes within our security logs or data set. So the common or most common measure of entropy is the Shannon entropy. And in general, a higher Shannon entropy value represents or for a variable indicates that there is more randomness in that particular variable, whilst a lower value suggests that there's less variety or more predictability in that variable. Now, when we talk about the Donsker-Varadhan theory or theorem, it is a fundamental result in large deviations theory, and it is often used particularly concerning the rate function for empirical measures of Markov processes. Also, it provides a way to quantify the divergence between a probability measure and a particular reference measure, often related to how unlikely certain empirical distributions are under a given process. So with that being said, we'll move on straight to our codes. So when we look at our codes here, I obtained data from the Kaggle website, and I'll show the Kaggle website here. So this is the data I use for this illustration, the global cybersecurity threats. Now, this data is from 2015 to 2024. So if you need this data for illustration, you can definitely come to the Kaggle website. And there are several other cybersecurity data sets here. So I go back to the codes and I explain the codes. So in this first step, what I do is I import the data set I'm using. Then because the data is in such a way that there are some leading white spaces and lagging white spaces, I use this line to trim the leading and lagging white spaces. Then following that, what I do is I compute the frequencies of the variables or the incidents of interest, and I also compute their probabilities because I need these probabilities to be able to compute my Shannon entropy or my entropies. So having computed the probabilities in this set of lines, I write a function for the Shannon entropies. And in line 29, I enforce or ensure that no probabilities of 0 would be in there. So I ensure that the probabilities are all greater than 0 because the Shannon entropy formula requires that I have the log of probabilities times the probabilities, because this is the summation over that. And we know that the log of 0 is undefined. So we don't want to have 0 probabilities in there. So that is what I do. Then in this set or this chunk of codes, what I do is I write a function for the Donsker-Varadhan entropy, and then I set it to use 10,000 functions for optimization. That is one cool thing about the Donsker-Varadhan entropy. So I set those functions here. Now with the functions I set, essentially I use three different strategies for the functions. So the three different strategies I use for the functions, the first one is a standard normal distribution. So I set random functions with standard normal distribution. And then my next strategy is that I write functions with higher probability categories using the log of probabilities. Then the third strategy I use is I move on to more extreme functions with higher variance. So with these three strategies, it can help me to incorporate the deviations into the Donsker-Varadhan entropy. Now, with the Donsker-Varadhan entropy, my whole goal is to choose the maximum values. So I set the maximum values of the expectations. So that's what I do here. And then I ensure that I return the maximum values for the expectation and also return the entropy values. So here I select and name my variables that I want to analyze. So the variables I want to analyze are one, the attack type, the target industry, the attack source, and then this security vulnerability. So that's what I do there. And then from here, I create a data frame for my results on the Shannon entropy and then the Donsker-Varadhan entropy. And then I make sure I include their probabilities as well. So from this point, I can print my results in line 100 where I print my entropy results. But it's good for us to visualize them. So the first thing I do here is in the visualization one, I plot a graph of the outcome of the Shannon entropy and then the Donsker-Varadhan entropy to see which of the industries had a high entropy. And then in this visualization two, I have the entropy by variable type also being shown. Then I also select in visualization 3, I decide to select the variable with the highest entropy to be able to look at it in detail. So that's what I do there. And then I try to also visualize the convergence or the optimal function for the Donsker-Varadhan entropy. And I plot its optimal function using the ggplot here. So additionally, I show the convergence of the DV entropy optimization. Then in these 5 lines here, I try my best to print all the 5 plots out. So with that being said, I will move on and then run these codes. So I run my lines of codes here. So we are able to see our output here. So I begin from the very first output. So I'll enlarge these so that we can see them properly here. So this is okay. So we are seeing that this axis represents the Shannon entropy for the variables of interest. So we see for attack source, the Shannon entropy was less than 1.4, and then we are seeing its DV approximation also being slightly above 0. But we see here that the Shannon entropy was highest or largest for the target industry, where we are seeing that the Shannon entropy was far above 1.8. This was about 1.9 thereabout, and then its DV entropy is negative 0.008. So this is what we are seeing, and then we have the entropies for the other types of variables. So this is the bar graph that shows us these comparison. So we saw that because the DV entropy was almost 0 for these other sources, so we don't really see them here, but they are supposed to be here. If you see DV entropy, it was negative, to confirm, it was negative 0.008. So that was the largest in terms of absolute value. That's why we are able to see that here. So then we can say that the target industry had the highest entropy value. That is for both the Shannon and then the DV entropy. So our code further looked at the target industry. So within our data set, we see that these are the different industries. So we are working with an entropy of 1.944 for the target industry. The industry with the highest probability is the IT industry. But however, we see that the there is they are fairly uniform. Thus, we don't see a wide discrepancy among these industries. And then we can also look at this by overlaying our Donsker-Varadhan representation. So then we see that the optimal functions for these industries are being shown here in the negatives, with the highest being the banking sector, and then the associated probabilities are being shown here. So again, the IT sector had the highest probability, which we saw in the previous chart. And then this shows us the convergence of the Donsker-Varadhan optimization. Now, one thing we would note, or we should note, is that if we have convergence for the Donsker-Varadhan optimization, it is almost equal to the Shannon entropy or the Shannon uh, um, optimization. So over here, what we are seeing is that the green line captures the true Shannon entropy. And then this is the smoothened line. So this is an illustration of measuring entropy in a cyber security data. And the data that was used, we can see the component of the data here. So what we see is that the data has different countries. The data also has the years. The data has the attack type. The data has the target industry. And then we are also seeing the financial loss in millions. We are seeing the number of users affected by the particular attack for the specific country, for the target industry. And then we also see the attack source, that is, if it is known, it is written here. And then we see the security vulnerability type also being shown here. And then we see what defense mechanism that is being used. And then we also see how many hours it took for the incident to be resolved. So thank you very much. See you next time.